Um, um, okay, great. Okay, hi everyone. I am El China and I will be your lecturer for Infi Echad and also another course, right?
Yeah, linear.
Linear, right. Okay. And but today I'm going to speak about calculus. And I said Infi Echad, that's in Hebrew, that's calculus. So a couple of questions before we begin. This is your second semester, right? What did you study at the first one? Discrete and computer science, right? Okay, great. Oh, so you didn't learn discrete mathematics?
This is my first time.
So that's
Because like people that are outside of the English program can also come. It's not only. Technically speaking, I'm in the Hebrew program.
Oh, I see. So you study discrete mathematics עכשיו?
Yeah, I'm starting.
Oh, okay. Another question is, I'm not sure about you guys. Are you just studying here the bachelor degree, or are you planning to stay in Israel? And I tell you why I'm asking. I'm not from immigration, right? But it's. Do you have some level of Hebrew, or is it complete zero? Or you plan to get in some level of understanding Hebrew? And I also tell you why I'm asking that, because the lectures will be completely in English, no problem, but a lot of the helpful material that I have is in Hebrew. So if that would be a huge problem, we'll think what to do about that. But that's what's the case. You don't have to answer me, that's why I asked, because some of the mostly exam from the past are all written in Hebrew. So I might be able to translate a few to help you, but certainly not all of them. So we should know that. Yes.
I think the lowest level we have is Ramaki, where we're on right now.
Yeah.
I didn't get
The lowest level of Hebrew we have right now is we passed Ahmed in last semester in Olivan.
I see. So I think it's enough. Okay, I get it. And I don't know what are the levels in the Ulpan, but any level is something. And
For reference, the level for someone to study in Hebrew is they have to be Ramachei. The way the program works is that you can start with zero Hebrew, and like the summer before the first semester, you do Aleph, Bet, Gimel, and Dalet in the summer, and then you can start doing Hebrew.
Oh, and that's my final question. I do require an answer for it. Are the courses you will take in the future will be in Hebrew or? So that's.
No,
So I should have started with that, because that means that not only are you supposed to be able to use some Hebrew, it's also important, because if I teach all the technical terms in English alone, you won't be able to know what the next lecture will speak about. Okay. So that's that. Obviously, if you need any translation, you can come to me. The lectures will be in English, and that's for that. Before we start, some technical preliminaries. You have Lambda site, Moodle. I put in a few links there. Where am I? Let's see how that's that. So this is the link to the Zoom room. It's the same links throughout. So if you need for some reason to connect to the Zoom, that's the link. And the lectures board, I write the lectures using Word, and I save the file at a certain link on my computer, which is connected to Google Drive, and you have the full access. Second. opened the folders and it didn't update on this computer. I wonder why.
We have the link in the Lambda, it goes to the drive, but the drive is empty.
Yeah, I agree, but I opened the folders on the Google Drive and I'm supposed to see them. And I opened them on another computer, so that might be the thing. Didn't update yet? Okay, I'll fix that later. I wanted to be ready, so I made it ahead, but on another computer, for some reason it didn't update. I'll save it a bit later, hopefully it will update. So you will have a link to the Word file, and in order to watch the Word file, you need to download it to your computer and open it. Why? Because Google Drive allows you to just click on it and see it, but it doesn't work well with math at all. But if you download it to the Word on your computer, then it works perfectly. And every now and again, I will do save as PDF, and then it works on any computer or smartphone. And so that's the lectures. They will be here. I will enlarge it a bit so you can actually see it. Actually, I think that's enough. And I also record every lecture. It's on YouTube Live. And you have the link here. Let's look at it. Recording of the lectures. And then it goes to my YouTube account, to my live streams. And then you see it here. It will always say calc 1 and then the date. So you will have it for eternity or until Google perishes. And it's live now, but the recording stays there. Okay, in perpetuity. And what else? This is the helpful material in Hebrew, so that's why I say it's in Hebrew, but you have tests from the past with solutions, and also it goes through the syllabus. And in short, it says it's not a book, but it says what are the subjects that we're going to learn in what order. And we also have videos, and the videos are full. They contain the entire lectures, but they are in Hebrew. So whoever it's helpful for them, I suggest you do use it in order to learn Hebrew, but in order to learn the subject, it may confuse, the Hebrew may confuse you. And so I think these are all the technicalities I wish to talk about now. Do you have any questions before we move forward? Okay, let's see if the Google Drive synced already.
I have a question.
Sure.
Where did you buy your tie?
Oh, I have, okay, you will see, I have, I don't know, more than 300 ties, so it's like a collection.
For real?
Yeah. And then it's from the internet, my wife orders them. And
That was great.
thank you.
You have one for every day of the year.
Not for every, yeah, I just got a matzah tie for Passover, but not for every occasion yet. I'm working for that.
Very good here.
Okay, so I will save it somewhere and then later I will see about the sync. But I need to save a compress every now and again. So let's put it here. One, and I'll move it later. Excuse me. Okay, so we study calculus, obviously. We study calculus in this course, which is called calculus. And I may have a lot of spelling errors. You feel free to correct me if you want. I try to have as little as possible. So we study calculus, and what is calculus? What is it? That's a question for you guys. What do you know about calculus? What is the subject?
Calculate something.
That's arithmetic, right?
I think in other places called mathematical analysis, you just
Analysis, yeah, right. In Hebrew, it has many names as well. It's called infi, חשבון infinitesimali, or analiza, which is analytics, right? Or chedva. In Hebrew, we say chedva a lot of the times. I don't know if you know it. So again, I asked, what is it about? Did you learn some calculus in high school, or so? Tell me subjects that you know from calculus. Yes.
Differentiation and integration.
Differentiation and integration. Great. In Hebrew, it's chedva, which is חשבון דיפרנציאלי ואינטגרלי. Okay. Calculus includes calculus includes differentiation and integration. And what are those? What are those?
Analysis of functions. You can for differentiation, you can find the rate of change of a function at a point.
The differentiation part talks about derivatives, which is the rate of change of a function. I agree with it completely. And in physics, it's still the rate of change, right? But what kind of physics term study the rate of change? So not acceleration, the velocity, the speed, right? Acceleration also, but that's the second derivative, right? And it's velocity, with C?
Yeah.
Velocity, and so forth. Because there is acceleration, but it's not a physics course, I won't talk too much about it. But it is important to speak about it, because that's the reason calculus was invented, right? It came from Newton and Leibniz in order to answer physics questions, right? So derivatives is the rate of change. The differentiation is derivatives, which are the rate of change. But basically, differentiations or the derivatives. Okay, that's what I'm trying to get at. What is the integration?
The antiderivatives area.
The integration has two different known meanings. One is antiderivative, the opposite of derivative, right? If you have a function, you derive it, you get to the derivative. If you integrate it, you get to the original function, right? What else?
The area under the graph.
An area. Okay. One, that's what I'm getting at. One of them, I would say this belongs to differentiation, right? Because I'm talking about derivative, antiderivative, it's still part of the differentiation for me. The area is a geometrical value, right? And is it the only geometrical value integration calculates?
No, you do volume as well.
What again?
Revolution.
Volume, no. Volume, what also you said before?
Just
So distance is a bit confusing.
Display.
Again? No, that's two physics. Distance, I would say you don't have calculus, you don't need calculus because the distance between 2 points you have Pythagoras theorem, right? But not distance, what?
Square.
No. The area, let's say the area of the shape is two-dimensional, right? The volume, what is it? Three-dimensional. What is one-dimensional? So the distance is one-dimensional, but it's not very interesting. What is one-dimensional and is interesting?
Line.
Path and you're answering geometry. If you have a shape, you have its surface area, surface is something else. You have the area, and what else do you have?
Perimeter.
The perimeter circumference is the word I was looking for, but volumes, and I don't know how to write it, circumference, I'm guessing. Looks good. Volume, circumference, and then surface area, which I said by mistake because it's also an answer. If you have a sphere, three-dimensional sphere or a ball, you want to know what is its surface area, right? So it is two-dimensional, but it lives within a three-dimensional world, right? So I don't want to scare you too much. All of this material will not be in this course, okay? But for me, integration is the measure of these geometrical values, and we learn how to find them using the antiderivative in the next course, right? And also in Einstein calculus time too, and also you will probably stay within area and maximum circumference, and that's it. In order to learn surface area and path and stuff like that, it's usually more advanced courses in calculus, which computer science does not have. But it is important, in my opinion, to understand where we're standing, right? So integration for me are the geometrical values. When in history, did man find these geometrical values?
Geometrical values for what?
Area, surface, circumference. Okay, that's Euclid, right? Euclid at about 300 BC, right? And before it's even more, 2,500 years, 2,300 years, something like that. Okay, when was calculus invented?
1,500 or something.
1,600.
It was like at the same time by Newton and some
The 17th century, by Newton and Leibniz. And what I'm trying to tell you at this opening is that how much time passed between minus 300 and 1600, almost 2,000 years passed between the two things. And now for us, integration, differentiation, obviously it's the same subject. I'm trying to convince you that it's so not obvious, right? You have geometrical question, and even in high school, you know how to find the surface of a circle, the area. I need to stop saying surface. What is the area of the circle of the circle? Yeah, pi r squared, right? And the circumference is 2 pi r, and this is known for a lot of time, a long time, way before differentiations and derivatives, right? So why did the two come together? because it was found out by Newton and Leibniz that you are able to find these geometrical values using derivatives. So it's not a part of this course. We will speak about derivatives, but it is the main frame that we're working. And in calculus 2, you will speak about it a bit more, and you will see the connection. You will define an area of the graph, and you will prove that it has a connection with the derivatives in the next course. We'll start with the basics. Okay, so far? And also, as the opening for the course, I want to show you a bit of Euclid's work, was right on the money. Before I show you, I'll ask you, what would you say is the most basic notion in calculus? The tool which with everything with which we study all subjects. What does differentiation and integration and everything in calculus have in common? Which basic tool?
Algebra.
No, I know. I did algebra is I think something that's is special for calculus. What is the delta you mean?
The rate
Small
of change.
difference, right? No, the small difference. The rate of change is when you take the quotient of two deltas, right? Delta y, delta x. But each delta which tends to zero, and that goes to my answer, limits, right? Limits of function are the basic thing which you use all the time. In any case, my point is that Euclid spoke about limits in different terms, and I will show you how. So this is from Euclid Elements. This is the book he wrote, again, 300 BC. And what is the claim, proposition that he proves here? And he said, circles are to one another. He means the area. The quotient of the area of two different circles are as the square on their diameters. When I asked you before what is the formula for the area of the circle, you say pi r squared. You didn't use diameters. What did you use?
Radius.
The radius. But it's not a big difference, right? Because the diameter is 2 times the radius, so squared is 4 times the radius squared. So the quotient will still be constant, but instead of pi, it will be pi over 4. Doesn't really matter, right? But that's his claim so long ago, so much before calculus was invented. And how did he do it? So what he did basically, he first of all proved the similar theorem for polygons, which is the shape with straight lines. Why is it easy to find the area of a polygon?
Because lines are usually the same length.
Not enough. I claim that each and every one of you can find the area of a polygon, which with a little help.
Can divide it into triangles.
In the triangle, exactly. You take that center of the circle, and then you have triangles, and the area of the triangle is easy. So it was easy for him. He was able to prove this result for the polygons. The quotient between the different polygons. He wanted to prove it for a circle. He was able to do it for polygons, right? So what is the difference between the area of the circle and the area of the polygon, right? The difference are all these parts, right? How can you make this difference infinitesimally low? how can you make the difference between the circle and the polygon really low? Yes.
So in polygon, infinite.
You add more and more nodes to the polygon, exactly, and that's exactly what he does. He says, take A and B and take the middle section between them and add O, R, Q, and P. And now we have twice the nodes, and the area of difference is much lower, 2 times lower. Not exactly, but okay. And by cutting the circumferences remaining behind in half and doing this continually, that's, and you will see in this course, the very definition of limits. Okay, it's not exactly the very definition, but it's very close. I will show you, I will come back to it in the future. And that's the way he proved this theorem. He said, if you do it enough times, it will be too low and you get a contradiction. The very thing is impossible. In Hebrew, we say stira, contradiction, and then he finishes his proof. So the idea of limits was already there in 300 years BC, and that is the main thing that we will learn this course. Okay, and I will write that. The main tool which we will study is limits. Okay, and it's important to understand because we will see in high school when you start learning calculus, you get to derivatives real fast. Here we will get to derivatives by the third part of the course. You say, how can we for so long speak just about limits? I tried to convince you that it's the right thing to do. The main tool, the brick of calculus are the limits. We will study it very closely and very accurately. And then we will be able to blow out and move to the next thing. And in calculus 2, we will move. We will go out even further, right? We will move even faster. But for some time, we will speak about limits. And in the first lecture, which is today, we won't even define limits yet. Okay? So that was the introduction to the course. And now we will move to the first subject. You will see as you study with me for every subject I teach, I start with some introduction to show you why do we learn this subject and what are our purposes. And so this is the introduction to the course, and now moving on to the first subject, first chapter and numbers, okay, and in that first chapter I will start with an introduction. Okay, that's the basic thing. And in Hebrew, if you wish to see the different chapters, you have it here. The first, it's one of it's numbers and well, for some reason I didn't prepare the English term. Numbers and boundaries, I think. And because today I will only speak about numbers, but as the first chapter, it includes the boundaries as well. The next one will be sequences, mostly the limit of sequences. And again, you might ask yourself, but we are interested in functions. Why are we studying sequences? Because limits are what we are interested in. And once we have the notion of limits in our head, it will be easy to make the transfer from sequences to function, and then series and whatnot. That's a long way ahead. Yes.
But also that sequences are essentially like alphabets or functions.
Yes, but they are not real functions, they are functions from the natural numbers. So that makes them much easier to study, but less interesting to use. But yes, the connection is there, and we're building up. That's exactly what we're doing. I'm just saying it because for many students, it's so weird that in high school calculus, you start where in the end of the first semester in a other way. So I'm preparing you mentally for that. Okay. And so I'm starting even earlier at numbers and I will do an introduction as I said, but my purpose here is to show you that even with numbers and arithmetics, limits are involved, whether you know it or not, and we will see. Okay? So what are numbers? What are numbers? Not a mathematical answer. What will you say to your children, your children yourself in the future? And what are numbers? An easy explanation, simple explanation. What do you think are numbers? What,
What you count with?
something you count with,
A system of enumeration.
count and enumeration. In Hebrew, I don't usually get this answer, but okay, yeah, but it's obviously correct, but I think it's something to do with the language. Count and enumeration, okay? And what else? What is next? Because counting, I'm telling you where I'm getting at. Counting is 1, 2, 3. But not, these are not all the numbers, right? What else can you do which is not called counting or enumerating with numbers? Negative, and what else?
Calculations.
Calculate what?
Numbers.
Floating point numbers.
But that's not the point, right? That's a tool.
Yeah.
What is the, I don't wish to say the word I'm looking for yet. But what do the numbers represent? That's a good word, yeah?
Integers are like basic for counting. Others like not negative are for something like money or something like that.
It's a representation.
So
It's a representation of the world.
a way to measure
I
different quantity, that's the word, thank you, quantities. Okay, kamut, I would say is kamut. And okay, and you said money, that's explain about your psyche and why are you in computer science. But it could be a distance, and it could be energy, and it could be anything, right? Measuring quantities. And what are the different quantities? So you have the natural numbers, which you can argue if they contain zero or not. For now, it will not. 1, 2, 3, 4, etc. Right? These are the natural numbers. And after you have, these are the counting, the enumeration. And after you have the numbers, which measure the quantities, what do you do with? You have, I don't know, I have a quantity of 3 apples, and I bought in the store another quantity of 4 apples. What do I wish to do with these 2 quantities? Sum them up, right? I want to do addition, and I want to do arithmetics. And then we wish to do arithmetic operations such as addition and multiplication, okay? And after we have the operations, we wish to solve problems, because that's what is math is about. It's having a model of some real problem in the world, at times we study pure mathematics for pure mathematics, but originally they wanted to solve real problems. If I talked about Newton, he wanted to measure the movement of the stars in the sky, right? So we wish to solve real problems, and real problems give rise to equations. So for instance, if I want to ask, if I have 3 apples in my refrigerator and I need 7 apples for an apple pie, I would ask, how many apples? What is it? So how many apples do I need to make an apple pie? And the answer is obviously 4. But if I have 10 apples in the refrigerator and I need 7 for a pie, are natural numbers able to solve this equation? No, right? So we go to the whole numbers or integers.
Yeah, in English, I think
Integers.
whole numbers is just natural numbers with 0, but I don't remember exactly.
It doesn't really matter for the course, to be honest, but integer numbers. So the integer numbers includes obviously 0, that's not a question, and also the negative quantities, which is a quantity with a direction. Usually when you say quantity with direction, what do you think about?
Velocity.
It's vectors, right? Numbers are kind of vectors, but you don't have too many directions, right? You have right and left, unless you get to the complex numbers, which again are not part of this course. But they are part of linear algebra, which I teach. So, okay, we'll get there. And can now can I solve any equation? Obviously not. No, obviously not. The answer is not. Say I have 4 children, which is true, and I need to divide 7 apples among my 4 children, and you will say using the integer numbers, obviously you can. So you go to the quotient number, the quotient numbers,
Rational numbers.
rational numbers, right? Rational numbers. It's quotient because of its name, but you write rational numbers and which are all of the quotients P over n such that P, the numerator, is an integer number, and n, the denominator, is a natural number. Why do I say what's the difference between the natural number and the integer numbers?
That it can be 0 and it can be
Yeah, exactly. So I don't have a problem with having negative numbers at the bottom, but 0 I dislike. So the way I write it, I took 0 out of the natural numbers, and then this definition makes sense.
Is that why there's such a strong debate about
It's
whether
not-
0 is contained in natural numbers because it's used?
Not just here, no, because you can write, I could have written P over Q where Q is different than 0, right? But it is tough like that. In many, when you have in many different definitions, say, and not 0, it's cumbersome, right? So it is kind of like that. It doesn't have any real meaning, but it is cumbersome to include or not include 0. But it's a silly debate, to be honest. In any case, I want to reiterate this definition because it's the first one which is a bit more confusing. What do I mean? Here I just wrote in the set different numbers within this set. 1, 2, 3, 4, and here 0, -1, and 1. But here I wrote something entirely different. I have 2, I don't know, compartments within the set. And divided by a line, and that means something. And how do I read such a thing? I say it's all of the elements of this form such that this condition holds, okay? And the conditions, which is a formula you study a bit in discrete mathematics, I believe, but it's not that much matter. It doesn't matter that much. So it's all the p over n such that p is an integer number and n is a natural number. But that's not a good definition, and I will tell you why. Do you agree that half 1/2 is a rational number?
Yeah.
Yeah, right? The p is 1, the n is 2, perfect. Do you agree that 2/4 is a rational number? Oops.
Yes.
Ah. Yes. What is my point?
Same thing.
They're the same number, but half equals to 4, and this equality and this equality has no Q, no, not Q, has no mention in the above set. So my point is that the rational numbers are not defined by this set, right? What are they do define by? We don't define them properly here. I assume that you know the rational numbers, you know how to add and multiply fractions, right? But there is something here to be desired. And it's very important to me. A lot of things I do not prove because they are not the main thing of the course, but I do want you to know that this thing is supposed to be well defined and proven by some mathematician who has the time and motivation. Okay? And you will see I will get back to half and 2/4 in a few moments. So we have the rational number, all the quotients, all of the fractions of integer numbers. And are there any other quantities other than rational numbers?
Yeah.
So, and why do you say yeah?
Because sometimes you have 4 children and you have to divide the square of 2 apples between them and
Sometimes you have in your refrigerator. Sorry, you might be choked. A square of 2 apples. You say that's what happens to you.
yeah,
Yeah,
once in a while.
I go to the store, can I have a square root of 2 apples? Okay, no, but okay. So the square root of 2 is the main thing. Okay. 2 things. One, the square root of 2 does not belong to the rational numbers, as we will prove. That's one thing. But the second thing, and that you failed miserably at, is why do we assume, or why do we need such a number to begin with? Right? And the answer is not that you bought the square root 2 of apples at the store, right? So why do we wish? So it's an entirely different question. Why is the square root of 2 not a rational number? We'll prove to you in a few minutes, right? But so what? Okay, so maybe it's not a quantity. Why do we want the square root of 2 to even be a quantity? Do anyone here know? Why do you think? Yes.
I don't know, eventually into Greeks.
Yeah, okay, so no, it wasn't the reason, but if you mentioned ancient Greeks, I will start with them. And the geometrical point of view of, so that's Pythagoras, why?
Oh, it's a diagonal.
Yeah, exactly. Say if I have a triangle, a right angle triangle, which has the distance of this edge one, and this distance is one. So say this is thick, right? So according to Pythagoras, Pythagoras theorem, c squared equals 1 squared plus 1 squared, agreed? Which is 2. So the length of the hypotenuse, if with hypo, the length of the hypotenuse is supposed to be square root of 2. Agreed? So that's a geometrical standpoint. But we are not in geometry class, we're in calculus. Does calculus have such a, because you may say, okay, when you want to measure geometry, work with something that, the real number, something that have a square root of 2, but maybe calculus you can stay with the rational numbers. Okay? It won't be true because as I say, calculus helps us with geometry, right, in integration. But there is a pure calculus question that is important for this, and you'll see. Suppose, so calculus, yeah.
Could it be when you're trying to work out the rate of change of root of x?
But that's two calculus. Because no, the root of x, it's not clear that it's existing, right? We are questioning whether do we need the square root of a number. Okay, so you can say this is the function, you need to work with that, because then I will say, why is this a function? Who needs it? I will do something a bit else. Suppose a train, an infinite train, but it doesn't really matter, follows the graph of y equals 0, right? The x-axis. Suppose a bicyclist follows the graph of y equals x squared minus 2. And both of these graphs do not mention any number other than the integer number, right? So you can create such a problem just with the normal numbers, the integer number, least of all the rational numbers. And my question is, do they meet? Intersect? So it's not clear for me that they meet. Algebraically, you will say, okay, x squared minus 2 needs to equal 0, and that's where they meet, right? But what I wish to say is something a bit less. A bit else. Something else. What is for the bicyclist? Y of x equals x squared minus 2, right? So what is y of 0 for the bicyclist? Where will it be when x equals 0? Where is the bicyclist? Minus 2, right? And what and when x equals 2, where is the bicyclist? At 2. So let's draw these 2 points. So the bicyclist would be here and here, right? Where is the train? The train is all the way on the x-axis, right? And now looking at the same question from a different point of view, do they intersect? What is your gut telling you?
It has to cross 0 at some point.
Yeah, you expect one would expect an intersection to occur where when x squared minus 2 equals 0 or x squared equals 2. Okay, and this is the mean value theorem that we will learn and prove in the future of the course. But that's another reason for which I want such a number to exist, such a quantity that squared being squared equals 2. And now I will formalize and prove the first theorem in this course. And
Square root of 2 is not the quotient.
theorem. So I wish to say that the square root of 2 is not a rational number. The problem with saying it like this is that you're not sure that there is such a number even. So what can I say accurately? There does not exist a rational number x such that x squared equals 2, right? I didn't mention square root of 2 in any case, but I claimed that there isn't a rational number that when being squares gets to 2. That means something is missing. And how do we solve this problem? We'll speak about later. But for now, I convince you that we wish there to be a solution, and in the rational numbers, there is no solution. I didn't convince you of that yet. I wish to prove it, right? So proof. Yeah. Assume that there exists such a number x, and we will see a contradiction. Thank you. And so if x is a rational number, what are the rational number? What is x made of?
There exists that p is an integer.
It's a fraction of an integer numerator over an integer denominator, natural denominator. Okay, write x equals p over n. Okay, because it's a rational number, it is allowed, right? Assume I'm not sure how you say it in English. In Hebrew, it's shelo metzumtzam.
It's Minimum common denominator? How do you say?
Least common denominator.
No,
No, but it's not that.
Not density, it's
Like
What's the question?
half
reduce.
is a shevel metzumtzam in Hebrew,
It's
and 2/4
the most factor.
is not, yeah.
minimal expression,
Yeah, I know, in Hebrew it's really,
what?
Simplest form.
Simplest form, yeah.
yeah,
I thought,
okay. Language has so much to do, some people say it's only the translation, no, because shevel metzumtzam is something that every boy in Israel learned. And when I say, is this shevel metzumtzam, everyone know it's not. So maybe in English, it's the simplest form, whatever. But I want to tap into something you already know, right?
what is the literal translation of shadow?
It's
Shadow is a fraction and tzad is to like minimize.
Yeah, but it's not exactly
But
because
it doesn't translate like.
yeah, the tzamtzem is to divide the two common factors. In Hebrew, it's a word, but tzamtzem. If you have 3a equals it's 6b, you can divide by 3. So in Hebrew, we say netzamtzem b'shalosh. Yeah. Simple form, whatever. But do you agree that each number, that's not the main point, do you agree that each rational number has simple form, which you cannot factor out anything else? That's important.
irreducible fraction.
Irreducible, yeah. Irreducible. Simplest form, okay. Or irreducible fraction. Okay. So we assumed that x squared equals 2. Remember, we said this is a solution. That's our assumption. So p over n squared equals 2. Agreed? So p squared over n squared equals 2, right? So p squared equals 2 times n squared. Taking a breather for a second. Do you agree with each step? This is the kind of proof which blows your mind. First of all, because you understand it and you will agree with it. But the second is we are used to having math with steps when you know what should be the next step, right? This is the kind of proof that occurs a lot in mathematics. That you would say to yourself, I would have never think about writing instead of x p over n. I agree that it is true, but why did you do it? I don't see why. And for this, and this question will rise a lot during the courses. I believe you saw it in discrete mathematics already. But the simple answer is such. You're not supposed to be able to think about it on your own. We study here 2,000 of human excellency, right? People thought about these things for many years. Like I said, it annoyed the Greeks. The Greeks, Pythagoras and his guys lied about it when they found it. They said it's not true, there is no such a number, even though they knew that there exists one. So you're not supposed to discover all of this math by your own. But after you see such proofs, first you need to understand it, and then you need to be able to reconstruct it sometimes. This specific proof is not that in the heart of calculus, but what I'm saying is for other proofs that will follow in the course. So it's not clear where I'm going with it, and I'm just saying it's completely fine. It was very hard for humans to get it, right? So I got to the fact that p squared equaled 2 times n squared. What is 2 times of a natural number?
An even number.
An even number. That's an even number. Even. So p squared is even, and therefore p is even. Do you agree about that? Because an odd number squared is an odd, so p must be even. So what does it mean that the number is even? It's 2 times some natural number. Agreed? Again, it's not clear why am I doing all this, but you will see very soon, and we're almost finished, believe it or not. So P is 2k. Let's substitute P into P squared. What will we get? If we substitute 2k into P in this formula, what will we get?
For k squared or?
Yes. And substitute. And you get 4k squared, right? Equals what? 2n squared, right? Wait, now what?
N squared, so that's.
Divide by 2, 2k squared is n squared, and similarly, n is even. So both the numerator and the denominator of x equal p over n are even
Or reducible.
contradiction, right? Because we assumed the fraction was irreducible. Right? We assumed we took an irreducible representation of the fraction. Agreed? So it's fraction. Hebrew is the same word. Shvarim.
Yeah.
We have the joke that older brother teaches his brother Shvarim. Okay, fractors. Okay. So we see how this proof, which was not straightforward but obviously true, shows that there couldn't be any rational number that being squared equals 2. That give rise to the real numbers. What are the real numbers?
Numbers that can be represented as fractions.
No, that's the rational number, right?
Sorry,
The real number, the next set, because we said square root of 2, we don't have it, we need it, so we enlarge our set, right? Like we did up until now, but now we're doing quite a leap. Yes.
Yeah, we add irrational numbers.
Yeah, but what are the irrational numbers?
Because people in some equations says like I don't know how to do it. I will.
It's not rational. No, I didn't mean why do you call it irrational? It's irrational because it's not rational. It's not. It doesn't make sense. It's rational from the word ratio, quotient. It's not from. It's not מספרים הגיוניים. It's quotient. But I didn't mean what to ask what is its name. What are the real numbers? And it's hard to answer because you don't know the answer, you never learn it. We'll also not really learn it here, because we didn't even build the rational number, much less we will build the real numbers, but I would say such. The real numbers are all the decimal fractions, including infinite representation. Okay? For instance, 0.1 is a real number. It's a decimal fraction. Agreed? What about 0.333? Also a real number because it has a decimal representation, maybe with infinite number of digits. Agreed?
Is this also a quotient number?
Yeah.
Yes, agreed. You're completely correct. You're completely correct. In fact, the natural numbers are part of the integer numbers, which is contained in the rational numbers, which are contained in the real numbers, definitely. Okay. So what number else would be there? Square root of 2, which is 1.41, etc. Also a real number, right? Now the etc. here is quite convexing. What are the digits? We have no idea. But we assume there is such a number. We will prove in this course that there is such a number, but we can never write all of its digits because it's an infinite amount of digits. Okay, agree so far? So now I want to show you why is that not a good definition. Similarly to the way I did it with the quotient number, the rational numbers. Right, the following question. The number 1, is it a real number?
Yeah,
What is its decimal form?
1/1.
No, decimal form.
Decimal.
1.00000 to infinity. Great? It is a real number. And I also said that the natural numbers are part of the integer numbers, which are part of the rational numbers, which are part of the real numbers, right? So 1 is a real number. Also, there is a number 0.999 to infinity. This is a real number, right? It's a decimal form, a decimal representation with infinite number of nines until perpetuity. What is the word?
Yeah.
Perpetuity. Okay.
Perpetuity.
I mean, yeah,
Perpetuity. Okay.
it's more like a legal one.
Yeah, okay. So my question is, I'm not asking whether these two numbers are real. They are obviously real by our definition. Are they equal? And it's a reminder of the question when we had the rational numbers. I took the fraction half, 1/2, and I took the fractions 2/4, 2/4. I say these are two representations of rational numbers. But this is the same number represented in two different ways. Agrees? By the way, what is its representation in the decimal form? 0.5, right? So it's also a real number. But now I'm taking two representations of numbers, 1 and 0.999, and I'm asking you whether it is the same number or not. So now we'll take a short vote. One finger says, I believe these are the same number. Two fingers, I believe these are two different real numbers. Take a vote. What do you say?
Can we do 3 and say, I don't know?
So what is your guess? It's either one or two. One says this is the same number. Two says these are two different numbers. Okay. So some of you voted one way, other vote. Is this the same number or two different numbers?
Same.
Okay. So some of you must. I think some of you must have seen it before.
I
Because
mean, it depends on the frame of reference, like what's.
Okay, so I'm not giving you the answer yet, but how am I able to prove to you one way or another without defining the real numbers? The answer is I can't really, but what I can do is assuming you believe anything from high school, you will be convinced in the answer. Otherwise, you need to lose concepts which you use all the time. Okay? You have a question?
No.
Okay. So let's see, I have a few explanations and ways to look at it. And let's take the first one. Let's mark answers, entries. Let's take x equals 1. Define x equals 1. Good. Define x equals 0.99 infinite lines. Okay. What is 10 times x? 9.999, right? That's because we know that we multiply decimal form by 10. The decimal point moves one step to the right. Really? So what is 10 times x minus x? So on the one hand, it's 9 times x. You agree about that?
Yeah.
On the other hand, 10 times x minus x is 9.999 minus 0.999, which is 9. So 9x equals 9, x equals 1. And zoom out for a second, literally, x was 0.999, and the same x equals 1. So if you don't believe these are the two numbers, the two numbers are the same, I mean, then something along the way you think, no, this step is wrong. And these are the steps you learn how to do in high school, right? Yeah. Next explanation. Another. What is a third? It is before. What is the decimal form of the fraction third? 0.333 in perpetuity. Agreed? What is 3 times a third? 1. 3 thirds are a 1.
Yeah.
What is 3 times 0.333? 0.999. Agreed? And again, the numbers are equal. And last, what is the difference? Yes.
You're skewing it.
Why?
Well, because in the first one,
Yeah.
10x is like it goes infinitely long, but the infinity is a bit smaller than the first infinity.
There is no infinity that is smaller by 1. That's first thing. And secondly, by definition, every digit has a place and represents some sign. What do I mean? It will be the, I said last that it's another explanation. This digit says 9/10, and the next digit says 9/100. Each digit has some signs. All sizes are 9. And in both cases, right? It's not, there is no other quantity that follows in the other place. And it's a lot to do, it has a lot, your question has a lot to do with what I'm trying to say now. What is 1 minus 0.999?
0, 0, 0, 0. There's someone somewhere.
It's 0. And some students tell me, after all these zeros, after infinite number of 0, there is a 1. And then I ask, what is the quantity that this 1 represents? Right? You have to have some quantity. And suppose that there is such an infinitesimally close quantity, what happens when we multiply it by 10? Get infinite numbers of infinitesimal quantities. There is such a subject of non-standard analysis. but then I will go ahead, you said that the infinite number of 9 is different. How do you know when I write this, what is the infinite number, whether it's small, whether it's large? I just wrote 9.999, right? You enter a realm of uncertainty. And we need not, because it is the same number, right? We're so surprised by it because we're not used to it. When I ask you whether half or 2/4 are the same number, if I ask someone in the first grade, they will say, no, I see 2 different numbers. But we learn in high school that a half and 2/4 are the same numbers. But this we don't learn in high school, so we assume every 2 representation means 2 different numbers. Okay, I know I wrote last, but I take it back. After last, another thing. What is 0.999? So the first 9 is 910, agreed? The second 9 is 900, and so forth, agreed? So basically the number is the sum of an infinite number of numbers, agreed? That's where limits are incorporated into the numbers themselves, the real numbers. The rational numbers were not such a huge problem. The real numbers are a huge problem because the number has an infinite number of digits, which means by definition that it's the sum of an infinite number of numbers, which is called a series, and we'll learn about it in this course. But it's not just any sequence. Does anyone know what kind of sequence is this? It's a geometric sequence because it's 9/10 plus 1/10 times 9/10 plus 1/10 squared times 9/10 and so forth. Agreed? What is the formula? Maybe one of you knows for a sum of an infinite geometrical series.
You said 9/10, so.
It's the first number
Yeah.
times 1 over 1 minus the quotient. Okay, so not everyone knows this formula. In Israel, it's in the 5 יחידות נוסחון. But if you didn't see it, it's not that terrible. I will prove you this formula. That's why I don't always use it. That's why we're after last, right? But assuming that you believe that this is the sum, what do we get here?
You get 9/10, which because it's multiplied, you get 1.
9/10. Agreed? Which is?
How it gets cancelled out.
Yes.
So it gets 1.
1. Okay, and again, you got to the same. For me, this is the least convincing because it uses a formula which is a high-tech formula for us, right? What?
No, but because you need to know why.
Why is this formula, right? It uses magic.
Yeah,
This is the uses magic.
If you already know the formula.
Yeah, I agree. So that's why I show it, because some students find it convincing, but for me, it's the least convincing because it used the most convoluted formula of them all. The other one, what they use, times 10 moves the decimal point. In any case, these are the same number for many reasons. And the lesson that I wish to teach you here are that the limits are incorporated even within the numbers themselves, the real numbers, which comprise of infinite numbers of quantity, have a lot to do with calculus. And for further discussion about these points, what is how do you write discussion?
one S, then C, then two S's, I think. Fisca, without the D.
Wow, okay. I will learn English by then. Okay. Further discussion. How much is 3 to the power of 2? Right. But why? Why? What is the power of 2? What is the power of 2 mean? It's 3 times 3. Okay. What is 3 to the power of half? You know?
It's supposed to be,
It's the
yeah,
square root of 3, right? Assuming that there is one, we will not speak about it now. Now the real question. What is the 3 to the power of the square root of 2? Meaning, I show you I didn't show you, but I'm using the arithmetic operation of a power, right? So the exponentiation. And 3 to the power of 2 you know how to do, and 3 to the power of half you know how to do. But do you know the power of 3 to the power of square root of 2? It's supposed to be an easy arithmetic operation between two real numbers. And what do you think it is?
is it something like 9 to the power of the square root of something?
Why?
Because you square the square root of 2 and then make an operation after you get to 9.
I will do something along the line that you said.
3 to the power of 125. Sorry.
Do you agree about that?
Yes.
So what is the next step?
Multiply by.
So that's 3 to the power of 2 times half, which is 3.
No, that's not.
No, it's not.
That's right.
I agree that it's false. Why is it false?
To the power of half.
Because the power is intrinsic.
Yeah, I agree.
Value to it isn't.
First of all, this is obviously false. I wish to say why is it reasonable, but why is it false? A to the power of b to the power of c does equals a to the power of b times c. Agreed? Right? But however, a to the power of b times c does not equal a to the power of b to the power of c. It's a different thing. So we are not able to work with it. What can we do? We can say that 3 to the number of 3 to the power of the square root of 2 is 3 to the power of its decimal form 1.41, etc., etc. Agreed? Yeah. Let's look at the sequence. 3 to the power of 1. Can you calculate that? Yeah. Then 3 to the power of 1.4. Can you calculate that? How? It's 14 over 10, which is the 10th root of 3 to the power of 14. Agreed? And then 3 to the power of 1.41. Can you calculate that? It's 3 to the power of 141 over 100. Any finite decimal form is always a rational number. We disagree. You take all the numbers and you multiply and you divide by 10 to the right power. So you take this sequence and all these numbers you know how to calculate. You can it will be extremely hard, but you can calculate 3 to the power of 141 and then take the 100 root. But what is, and with that I will finish, what is 3 to the power of the square root of 2? It's not any of the numbers in the sequence, right? So what is it? We have the sequence 1.4 and then 3.1.41, etc. What is the place of 3 to the square root of 2 in this sequence? It's the limit of the sequence. So even calculating the power of 2 real numbers, even this arithmetic operation requires limits. So that's enough for today. I'll meet you at the next meeting.
Now, we are sitting here.